Ben Yu, a professor of electrical engineering at UC Davis. His research at UC Davis includes future internet, elastic optical networking, software-defined heterogeneous networks, and high-performance computing and networking.
Great.
Thank you.
Thank you very much. I was at the San Francisco conference, Optical Fiber Communications, and I got stuck in traffic, and I was like driving really fast and maneuvering, and just got here. I skipped breakfast, I skipped lunch, and they gave me a nice chocolate that says Wine County on it. So I just had all the ingredients for it, became very hyper, but it's very happy to be here. Thank you very much. Testbed and networking is really part of me. I'm like a fish in the water, and I really like to be doing testbed work. One of the things I did after my schoolwork is to join a company called Belcore. And at Belcore, we did the future network studies. And Belcore was the, when AT&T split off with Regional Bells, Regional Bells thought that they should have Bell Labs. So they formed the Bell Communications Research, and I joined there. And we did all kinds of really exciting research network studies, which happened to be, this was back in 1991, which happened to be really a software-defined network. As pointed out earlier, software-defined network is really not new. My company used to write 300 million lines of codes that were running the entire United States network. And it was just amazing to work with these 6,000 people at Belcore. But what was interesting is that I could not touch a single line of the code. It was a very closed system. And I think something behind SDN is really the openness. The open source is really powerful. So some of the things I'm going to talk about here is kind of putting things into historic perspective, but at the same time, looking at the future, what will be really new, and also kind of addressing the key important features of SDN. So I've been working on high-speed optical network, and one of the things that I realized is that when I came to left Belcore in 1999, joined UC Davis, was that the first thing I did was to knock on CENIC and knock on UCOP and said, we got to set up this high-speed network. And it took me 15 years to get here. And one of the reasons I joined UC Davis is because we had 144 fibers in the ground already back in 1999. I said, oh, this is, I'm the fish, and there's the water. I like to kind of jump around there. But it's actually very difficult to do this high-speed networking on SDN with high-speed networking, especially when you're thinking about kind of interfacing with the customers, clients, and applications, and have the application feed into reconfigure as SDN. Very, very difficult. So I'm going to just kind of go through step by step. As I pointed earlier, SDN is not really new. Back during the World War I, people talked about software radios and radios that can, cognitive radios that can reconfigure the receiver based on what's available. And now they're calling it software radios, and software-defined network is kind of extension of that, except that instead of just doing at the client machine, we're talking about centralized control plane that can work with all the client machines. But going beyond that, what we're thinking of doing is to look at cognitive network, and there's even beyond that is a knowledge plane network proposed by David Clark and so on at the MIT. So the highest level is kind of more an AI network. What we're looking at is kind of a network that can really adapt to the client's needs, customers' needs, and kind of situation aware. And all these things we're looking at kind of observe, analyze, and act type of cycle. And how do you do this? And the kind of, in the textbook, why the SDN is defined as separation of control plane and data plane. I said, well, this was all done back in 1980s and 1990s. We have done this already. And then separating forwarding and routing function, we've done that too. Virtualization of lower layer functions is also we have done before. So I think SDN is something in the sense that when telecom was all doing centralized control plane, data network, IP people all doing distributed control plane, when the future internet, next generation internet came up, we had to kind of come to a common place. And at least what I did in what I'm going to show later on was to introduce a lot of distributed control plane into centralized control plane. Whereas what IP people did was the opposite. And now the IP people are really excited about SDN, but a lot of the things we're talking about are the things that we have already done in the 1980s and so on. But what's really challenging in SDN is, can you really do high-speed, reconfigurable, software-defined optical network? Can you really support 100G customers, or maybe 400G customers? When Google has to back up their data once in a few days, can you actually transfer petabytes of data within a short amount of time without charging them petabit per second type of fees? I'm not talking about doing the switching at the electrical layer. If you have a lot of these line cards, Cisco people, Cisco is our sponsor, they'll love a lot of these line cards with a lot of these IP functions in it, but it's very power consuming and also expensive. So can you do this with the pure optical layer? Going beyond that, I mean, OpenFlow is very exciting and so on, but then there's a flow space limitation. Can you actually support migraine traffic of mobile and so on with a scalable layer 2 functions and so on? Going beyond it, can you actually scale this network with a heterogeneous multi-domain, not single domain? I think most of the SDNs people are talking about single domain. Now, can you have really multi-domain work with each other? And then can you now integrate application onto these type of future networks and have the application people really drive the network configuration and so on? Some of these things are kind of oxymoron in the sense that if you start to have billions of people control the network, you're going to have a problem. But these are kind of challenges of the future. So that's kind of very quickly going through historic perspective. When I joined Belcorp in 1991, we had something called ONTC project, Optical Network Transfer Consortium. There we had a hardware-defined optical network where a bunch of ATM switches. Do people remember ATM? Yeah, we have a bunch of these ATM switches connected to each other, optical. All the reconfiguration done by electrical ATM functions. You are supporting quality of service, everything at high speed. But it was a hardware-defined network. Now in 1993, we started a new project called MONET, where we support everything transparent, high capacity, low latency, all optical network, where the application can go directly down to the physical layer and go to optical connection and so on. And control plane, data plane, of course, separated. And then you had application all this supporting. It was kind of funny because it was transparent network, so that optical network was no longer having ATM switches to control the network, or the edge routers were not doing anything with control network. So then the joke was that, okay, we need to reconfigure this network. What are we going to do? I'll make a phone call to the central office. But wait a minute, central office is supposed to be on the optical network too, right? So in any case, there was a kind of fun stuff that we did. This was a $80 million project back in 1993 to 1999. I was running the testbed at that point, integrating testbed. It was kind of almost like a space shuttle project where President Kennedy said that by the end of 1960s, we're going to have man on the moon. Gosh, how are we going to do this? So then at the beginning, we did a lot of simulation. There was not even a company making these WDM switches and so on. So we're prototyping in the lab. We're working with the vendors. Vendors came back with these kind of gadgets. And we're putting these gadgets together in the lab and so on. It's kind of really, really fun stuff. But we're talking about these things at the hardware level, software, middleware, all of these things. And we're supported by AT&T, Belcorp, Bell Labs, and so on. And this is the testbed that we put together. My team people prototype the devices and systems, and there are companies who are making lasers, not necessarily WDM lasers, but we're able to work with them to kind of provide us with actual wavelength. We did a lot of simulations. When we put all these things together, what's exciting was that the network started to work really well. But at the same time, there were a lot of unexpected things, like we had channel power equalization, also kind of network power was like fluctuating each other. But here we have craft interfaces. Network operators sees many of these workstations. We have yellow for alarm and red for danger and so on. And we were having video conferencing and so on. It was really exciting. This was set up at Belcorp, Bell Labs, and so on. And then what we did was to move this testbed to Washington, D.C. Washington, D.C. had OC 48, 2.488 gigabit per second single wavelength ATD network going on. And then what we did was to increase the bit rate to 10G and also put 8 wavelength in it. Now you kind of laugh about it. 8 wavelength, 10 gig per second. That's kind of boring, isn't it? But back then, this was really reconfigurable, fully managed optical network with 10G. And then we looked around for the application. One of the downside of this industry network was that at the industry, we don't really have much applications to talk about. We're not running hospitals. We don't have teachers and so on. At our client nodes, DISA, DIA, DARPA, and NRL, NASA, and NSA, we had people who are interested in uncompressed HDTV. Back then, there was a competition between progressive versus interleaving, the progressive-based 1.5 gigabit digital video transmission. So we were able to demonstrate this low latency interconnect and so on. These are all based on software-defined networks. Now, in 1997, new DARPA project started called Next Generation Internet, and I wrote another proposal back then to integrate telecom network with the datacom network, where the centralized control plane of telecom meets distributed control plane of the datacom. And also, you remember those IP and ATM and SONET boxes? Each time you have these boxes, you have to pay for these boxes. And I said, we'd like to actually support the client. Dominant client is really IP, directly with optical. So going from kind of this multi-box to simplify, and then we said, we'd like to support customer or client traffic at IP directly on WDM wavelength with a thin shim layer called optical label. So then based on that, what we can do is to, again, have the software-defined network. What used to happen is that you have a bunch of this SONET and ATM and routers, all these boxes. And then what you have is that the optical network is just a dumb, fat pipe. Optics is good for you because it's dumb and fat. It doesn't not even think. But what we were trying to do back in MONET and NGI, Next Generation Internet, is to bring intelligence to optics. Instead of doing dumb, fat pipe with optics, we put the reconfigurability with WDM. So then you reconfigure the capacity, reconfigure the topology, depending on the needs. Now, this was the work we have done, again, in 1993 to 97. And then in 97, Sienna and those companies started off, and now these ROADMs and so on are being deployed in the network, but it took so long. And then here, going from this telecom network to the future next-gen internet, what we did was a slight enhancement of these network elements to something that can be packet agile or the rapid reconfigurable. So the idea behind then was that instead of just doing telecom-based centralized control plane, what we decided to do is to put the distributed control plane together. And what we did was that we put what we call optical label. Now, kind of bear with me. These are network elements running 4 or more wavelengths. But the centralized control plane typically...
Can you speak into the microphone?
Oh, I'm sorry. I forget that I was being broadcasted. Okay.
Yeah.
This one?
Yeah.
Okay. All right. Okay, let me just okay. So then what was going on was that these are 4 wavelength network elements, and there is a central control plane network called DCN, Data Communication Network. On the data communication channel, there was at 1510 nanometer. And then we have a data channel at 1550 to 1560 and so on. So what's interesting here is that we have a central control plane with a network control management. You can call it POX or NOx, or and you can have PCE and so on. But at every node, you have a distributed intelligence where you can actually forward the packet or kind of redistribute the locally based on the local needs. So what we have done was that we brought in kind of a telecom-like centralized control plane, which we called kind of like a brain-like. So it's very slow and elaborate. It looks at the whole thing and does performance management, security management, and looks at the anomaly, and then look at the entire picture and listens to instruct the reflex, where reflex is like a forwarding table, FPGA, and so on. That locally, it does very rapid and reflex-like reconfiguration. You can do packet forwarding and so on, and communication with brain. So you have, and most people here, I mean everybody actually here, have very good coordination between brain and reflex. And there was a concern that people thought that distributed and centralized control plane will not work well, but here we were able to demonstrate these were working very well. So then you can actually have a scalable and something that makes sense, but also something that can be proactive and react very responsive in terms of faster configuration. So we have set up the network. So the previous network testbed was upgraded to this optical level switching based testbed, where we have edge routers interfacing with the client network. So long as there's a label, you can actually have completely software-defined network that is centralized controlled as well as distributed controlled, meaning that central control plane can actually do kind of plain old telephone type of configuration where you can purposely configure the switches so that you can have end-to-end flow. At the same time, though, each one of those edge routers can put the label on a data or datagram or even circuit so that you can forward the packet very quickly. So the idea behind this network element or optical level switching router had this flow table that was controlled by network control management. Okay, sounds familiar? This is basically exactly what OpenFlow is doing. OpenFlow capable switches have a backport where you can connect with NOCs and so on. So there's kind of a way to enhance. In fact, there are now optical switches, like a MEM switches from Caliant and so on, having similar, Sienna has similar capabilities too. So now I'm going to move on to kind of the future. What we're doing today, we got a new GENI project, NSF project. We're submitting a new NSF project, and I hope many of us will work together with us, and we're looking for sponsors and collaborators. And COTN, CENIC OpenFlow Testbed Network is our key collaborator, and our new GENI project, and so on. So our new direction is to really think about multi-domain, heterogeneous network. Customers really don't care where you're using optical or wireless. They want really high throughput, end-to-end, low latency, reliable, and secure connection. And IP is really end-to-end principle. So whether the traffic is going through optical, wireline, or satellite, or multi-domain, the customers really don't care, but they like to have very good, again, secure and high throughput network. Then how do you support this multi-domain software-defined network that's not really well defined today? There are several ways of doing it. Most popular way of doing it is to have hierarchical network. So each administrative domain, so each autonomous system has hierarchical structure, so that multi-domain structure. But then, let's say AT&T network and the Verizon network and let's say T-Mobile network, they don't really like to have another hierarchy and say dictate. In fact, there's an activity in Japan that says, let's have the whole internet governed by one entity, and that's not something that most people are feeling comfortable with. So then the other way of doing it is to put peer-to-peer. So you have multiple SDNs and multiple administrative domains dictated through peer-to-peer, but this is awfully slow, and from our experience with the BGP, it kind of collapses, and once it collapses, it's a problem. What we have been working on is based on brokered method. It's kind of very interesting, and we have prototyped something that we'll be testing in our own testbed based. So that's kind of a brokered method is more market-driven, and it's somewhere between hierarchical and peer-to-peer. As I pointed out earlier, UC Davis, the reason I came to UC Davis is because there are 144 fibers all in the ground already. And now we have connected maybe about 20 labs, thanks to our IET people. Myself is in Kemper Hall, Node 2, next to the telecom network. And then you can then, because you have 144 fibers, you can actually artificially set up a lot of these domains. And this is our science DMZ, and we have visualization people, we have network for earthquake engineering, medical, and all this stuff. And then it also connects with the 100G production side of CENIC through the firewall, but also COTN without the firewall, and then we connect to ESnet and all these other collaborators of us. And a few years ago, CENIC was writing a GENI proposal, and I brought about 17 faculty members and supported and wrote proposal letters and so on. So that's a real network now. The COTN, unfortunately, right now is only 10G single wavelength and only point-to-point. And we hope that it's going to go up to 100G multi-wavelength and optically reconfigurable. But yet, it's a very good starting point. I just had a communication with San Diego where Larry Smart will be working with us on end-to-end traffic and so on. So then going beyond that, we like to connect this with the rest of the network, the GENI and international iGENI and so on. So one of the examples that we have here is to collaborate, our collaborators at KDDI and NTT, NEC, and Bristol University, and so on. So we're going to have multi-domain network experiment with optical and wireless involved. So then what kind of applications can we support? From the client, we have a lot of application people who have no idea what SDN is, but they like to use the good features of SDN. One of the key applications is really medical. The reason that I mentioned medical is that if you ask yourself, what is a key application that can benefit from low latency and high capacity? Or you may say, oh, why don't I do file transfer or file download from Google, maybe terabyte data, but it's not as latency intensive. Okay, and then we say, why don't I just watch TV? Why don't I watch Super Bowl with 8K? But even if Super Bowl 8K is delayed by 5 seconds, you don't really notice it. I think really the key is you want to have interactive, high definition networking. So if you have a visualization of, like say, 1,000, 1K HD TV, but 3-dimensional, 1K by 1K by 1K, 3-dimension, and 28 bits of color, 30 frames per second. That's actually about terabit per second real-time application without compression. But if you do 8K and so on, you're talking about 64 terabit per second and so on without income. But then there are more interesting needs in high-speed medical. When you have this telemedicine where 3 or 4 medical doctors who are experts in each area, then they like to collaborate and so on. Then we have interactive applications. Telemedicine is very exciting. And you like to also have this down to the ambulance. So then ambulance, wireless, and so how wireless and opticals work to support more than 10G. And California Telehealth Network led by Dr. Tom Nesbitt at UC Davis Medical Center, very exciting. So then going down to kind of high end, down to also low end, migrant traffic of energy efficient network. This is a West Campus, West Village, where we have a live test bed of people using the energy zero, net energy zero capacity, where we look at monitoring and so on. So just kind of quickly to wrap up, if you have a software-defined cyber infrastructure, going beyond network, so then there are applications of bringing the sensor network to data analysis, visualization, and then we can feed back the information to prevent, detect, and respond to recover from any environmental effect. But this software-defined cyber infrastructure can be useful for many others, like smart energy. The same idea, the same infrastructure supporting that application, again, software-defined. And then healthcare, as I pointed out, you can have sensor-based wearable sensors visualized, and then you can prevent and detect, respond, and recover from your healthcare issues. So this is kind of the last slide. We are having a GENI engineering conference at UC Davis on June 22nd to 24th. I hope many of you can come and see and watch and enjoy our new capability along with our collaborators. Thank you.